So now that we have seen the important connection that the elementary matrices make between invertible matrices and the row operations, we are now ready for this theorem, the pièce de résistance. This theorem is going to provide us with the best way to visualize an invertible matrix, as well as providing us with a method for computing the inverse of higher dimensional matrices. So get excited. So this theorem says that in n by n, matrix A is invertible if and only if matrix A is row equivalent to the identity matrix. Now in this case, any sequence of elementary row operations that reduces A to this identity matrix also transforms the identity matrix to the inverse of A. So this is a powerful theorem, not only for this section, but for a great deal of the rest of the course. So we need to verify that this holds true so that we can take advantage of the conclusions. So what exactly is this theorem saying, and what do we need to show? Well, an n by n matrix A is invertible if and only if matrix A is row equivalent to the n by n identity matrix. So there's two things that we need to show. We need to show that if A is an n by n invertible matrix, then matrix A is row equivalent to the identity matrix. And we also need to show that if matrix A is row equivalent to the n by n identity, then matrix A is invertible. So we have two cases that we need to look at here. Let's begin by looking at case 1. So here we go. If matrix A is an n by n invertible matrix, then matrix A is row equivalent to the n by n identity matrix. So to begin, let's suppose that matrix A is an n by n invertible matrix. So what does this tell us? Well, we know by a theorem from this section that if matrix A is an n by n invertible matrix, then for every vector B in Rn, we know that the equation matrix A times vector x equals vector B has a unique solution. Now, we know by the equivalence theorem that if this equation, matrix A times vector x equals vector B, has a solution for every vector B in Rn, that this is logically equivalent to saying that matrix A has a pivot position in each row. Beautiful. So, since we know that matrix A is square, so since matrix A is a square matrix, and since each pivot position must be in a different column, what does this tell us about these pivot positions? So since matrix A is a square matrix, and since each pivot position exists in a different column, then this lets us know that these pivots exist along the main diagonal. So then the pivot positions must exist along the main diagonal. Now, if the pivot positions must exist along the main diagonal, then therefore matrix A is row equivalent to the identity matrix. Oops, we did it! Woohoo! So this completes the first part of our proof, showing that if matrix A is an n by n invertible matrix, then matrix A is row equivalent to the n by n identity matrix. Woohoo! So, now that we've shown case 1, we need to verify case 2. So in case 2, we want to show that if matrix A is row equivalent to the n by n identity matrix, then matrix A is an n by n invertible matrix. So in this case, we want to begin by supposing that matrix A is row equivalent to the n by n identity. So let's think for a moment, what exactly is this saying? If matrix A is row equivalent to the n by n identity matrix, well then, this implies that there exists a sequence of row operations that reduces matrix A to the n by n identity matrix. So how can we think about this in terms of matrices? Well, we can say that since each step of row reduction is equivalent to left-hand multiplying by an elementary matrix, then there must exist elementary matrices that reduce A to the n by n identity matrix. So there must exist elementary matrices. We'll define them as elementary matrix E sub 1, elementary matrix E sub 2, all the way to that last elementary matrix, we'll say E sub P, such that if we take matrix A and perform the first row operation, then this is going to be equivalent to saying elementary matrix E sub 1 multiplied by matrix A. Now, if we want to perform a second row operation, this will become equivalent to saying the second elementary matrix E sub 2 multiplied by the previous step. And we continue with this row reduction process all the way to that very last elementary row operation, E sub P, multiplied by all of the previous elementary row operations. And this is going to produce or be equal to the n by n identity matrix. So in other words, if we left-hand multiply matrix A by this sequence of elementary matrices, so here's our sequence of elementary matrices. So if we left-hand multiply matrix A by this sequence of elementary matrices, then what we're left with is the n by n identity matrix. Beautiful. Now, since we know that elementary matrices are invertible, and since the product of invertible matrices is invertible, we can make the following conclusions. So since we know that elementary matrices are invertible, and since the product of invertible matrices is invertible, we can make the following conclusions. So we can take what we just defined above and multiply by the inverse of this sequence of elementary matrices. So we have the inverse of this sequence. So we have E sub P all the way to that last elementary matrix, E sub 1. And we're multiplying that by the sequence of elementary matrices multiplied by matrix A. And this is equal to the inverse of the sequence of elementary matrices multiplied by the n by n identity matrix. Now, since elementary matrices and their product is invertible, we know that this is equivalent to the n by n identity matrix multiplied by matrix A. And on the right-hand side, we know that that reduces to simply the inverse of the sequence of elementary matrices. Now, the identity matrix times matrix A leaves us with matrix A. So we've shown here that matrix A is equal to the inverse of this sequence of elementary matrices. And thus, matrix A is invertible. Woohoo! And this is invertible because it is the inverse of an invertible matrix. So matrix A is invertible, and that is because it is the inverse of an invertible matrix. Woohoo! So we have shown here that if matrix A is row equivalent to the n by n identity matrix, then matrix A is an n by n invertible matrix. But that's not it. There's more. So, to see the remaining part of this, I want you to think back to those useful facts about invertible matrices. So let's quickly recall the following property. Now, recall that if matrix A is invertible, then the inverse of matrix A is invertible, and the inverse of matrix A is matrix A. So let's go ahead now and apply this property to what we have above. So we can say that since matrix A, defined as the inverse of the sequence of product of elementary matrices, is invertible, then we know that the inverse of matrix A is also invertible. And we also know that the inverse of matrix A is equal to the inverse of sequence of product of those elementary matrices. Now, the inverse of this product is simply equal to the product of these elementary matrices. So E sub P all the way through to E sub 1. So then we are able to conclude that the inverse of matrix A is equal to this sequence of the product of elementary matrices, E sub P through E sub 1, multiplied by the n by n identity matrix, which tells us that the inverse of matrix A results from applying this sequence of elementary matrices, so elementary matrix E sub 1, elementary matrix E sub 2, all the way to elementary matrix E sub P successively to that n by n identity matrix, which is the same sequence that reduced matrix A to the n by n identity matrix. Woohoo! And so this completes the second case of our proof and the proof of the theorem.